Hi and welcome back to a new video. Today's video will be fully about Intel Arrow Lake delidding. From what I can tell right now, because I'm starting to shoot this video in August, it is the most extreme, most complicated, probably also most expensive delidder I designed so far, because it's very complicated to delid these CPUs in general, but seems to be also quite some risk involved. I already spent some weeks and months designing the first delidder. I'm already in the third revision right now, and today I want to start and try my first, hopefully successful delid, and at this point I'm not even sure if there will be a commercial delidder available, but we want to find out that together. Hetzner is one of the leading hosting providers and operates state-of-the-art data centers in Nuremberg and Falkenstein in Germany and Helsinki in Finland. Hetzner has established itself beyond Europe and is well known for self-developed high-tech products at attractive prices. One of Hetzner's latest products is the GEX 130 dedicated GPU server. The NVIDIA RTX 6000 8th generation graphics card with 48GB of graphics memory and 568 tensor cores is perfect for all your AI projects and offers enough power for compute-intensive projects such as training AI models. The GEX 130 is a dedicated server, so you don't use virtualized resources that you book in addition, but you have full access to the server and the GPU. Find out more in the link below. Already, I think in April or May, there were leaks of an Intel Arrow Lake CPU pictured. Looking at this image, I first was like, okay, that looks kind of doable. I already knew that those CPUs had to be soldered, so that wouldn't be a surprise, and also means that we will have to move the IHS to a site somehow to remove it from the die. But then in, I think, end of May or June, I received my first mechanical sample, and I saw that it's a bit different from the first and early leaked image. The retail CPU has one more set of SMDs in this corner, and that makes it very difficult. So no matter if you would go in Y direction, like plus minus, or X direction, doesn't really help. Even diagonal, if you would try to push like this, or even push here first and then to the right, it wouldn't help. There wouldn't be enough space to just move the IHS in one direction to release it. Yeah, so that's making it already quite complicated. It only leaves us with the same solution as with Ryzen 7000, that we have a slider that moves back and forth, uses metal fatigue to finally release the IHS from the chip. The only difference is that on AMD the chiplets are much smaller, and even though the Arrow Lake CPU consists of different chips, it still acts like a monolithic CPU in a way of delidding. Like, it's much bigger chip, much bigger surface area, and thus the delidding takes just much longer. And it's also still very, very tight clearance. I will show you this under the microscope. This is already the third mechanical revision. This was the first one. Here you can see the principle of the slider moving back and forth. You will put the CPU according to the triangle into the base. The final one will obviously be nice and anodized, but that's just like still prototyping, so it's missing the markings. The slider is not symmetrical as well, so it also has to be aligned according to the triangles. You put it in like this, and then theoretically this process will start. We're now looking under the microscope at one piece of the delidder. That's the view under the microscope, and that's just one of the parts. And if I just move the slider to the right, this will be the end position of the IHS. Same thing on the other side. If we slide it to the left, very tiny clearance. And that was also the original plan. Just move it mechanically back and forth multiple times. That's also what I did on this specific CPU, my mechanical sample, until the IHS comes loose. And that's how it's supposed to look like. You can also see the individual chiplets on here. And obviously, same as on the IHS, after delidding, there was indium solder on it that I had to remove, polish off, and that's how it would look like. At that point, I thought, okay, nice, I'm pretty much done with my delidder, looks all good. Revision 3 works fine, there's enough clearance. I moved the IHS back and forth plenty of times without damaging anything on the CPU. But as I pointed out in this video already multiple times, this is a mechanical sample. This means I received this CPU specifically to design the delidder, and it's non-functional, so it was already dead. So I cannot test it, and at that point when I received it, I didn't even have a motherboard. But then I received the message from Intel that the delidding risk that is involved in this CPU is extremely high. So they said that there is a potential very high risk of damaging your CPU if you're delidding these. And I've been doing this for a long time now. It's, I'm not sure, my 10th delidder or something. And Intel never said something like this before. They typically only say that, of course, this is some kind of modification, not covered under Intel warranty, maybe not recommended. But it was the first time that they specifically said that there's a very high risk involved. The only explanation I have for this is that there could be additional mechanical stress that is introduced into the CPU by moving the IHS back and forth so many times. And because this is a multi-chiplet CPU, that maybe something comes loose, something breaks, and thus kills the CPU. And I would take this warning serious from Intel. That's why I thought, okay, I have to come up with something different, because there are two challenges. The first challenge is the glue around the IHS. The second challenge is the indium solder that sits on the die. So I thought, I will create this thing. This is a heater for the delidding, because the only reason how I can think of reducing the mechanical stress onto the die is by melting the solder and then be able to release the glue by moving the IHS. So we have a delidder sitting in here. That's also still the first prototype. It will look a bit different, but right now, end of August, I just want to find out if there's a way to do it, like delid my CPU with this thing and keep it alive. And as you can see, important, it will heat up, so only use it with protective gear, with gloves, and put it on a fire-resistant surface. This is also a near finished version of the delidder. It's already anodized, just missing the laser engraving for the orientation of the CPU, which will be marked with a triangle, so you can find a triangle on your PCB and then you can align it accordingly. But apart from that, it also now has those things on top that keeps the slider down while delidding. The heater itself, in this case, is also still prototype status. There are a few things I still want to change. It's made out of PTFE, which is a high temperature resistant plastic, and it won't be a problem to heat it up. There's a heater element already in here. I already applied some thermal paste on top. The final version will also have a temperature sensor sitting in here that can make contact with the CPU from the back, so you can track the temperature, and then you put the CPU inside the delidder, then in here. Now the CPU is already in the delidder. Place slider on top. Just have to pay attention to the orientation, but I know it because I designed it. And now I will have to add these bars. And this goes into the heater. From the back you can see at the CPU, and in the retail state there would be the temperature sensor included that has contact to the back of the CPU. Well, you will have to force it onto the CPU, and that's very important. So it makes contact with the CPU itself, and then pretty much ready to go. In my case, this is also still very experimental. The heating element is just connected to my PSU, and it's also only heating with 40 watt, whereas the final one is supposed to be 50 watt, but you can already see it heating up. I think I forgot to mention that this is now a second CPU that I already tested, verified. We got some baseline numbers for the temperature, so we have something to compare to, and we now hope that it survives. In my first attempt of heating the delidder without a CPU, it took like 20 minutes to reach the temperature of about 160 degrees Celsius. Better would be about 165. In that region, the indium solder will be liquid and we will be able to move the slider and the IHS without any mechanical stress on the chip. So it will take some time, and I can tell you it's only the first out of 2 steps. After 5 minutes, we are already at 76 degrees Celsius, but I can tell you, you will need patience. Now after 10 minutes, already 117 degrees Celsius. We now exceeded 165 degrees Celsius, thus far enough above the melting point of the indium, should be fine and hopefully safe to delid now. This definitely reminded me of back then when CPUs were not soldered and there was like a click that released the glue. You can see IHS is loose. Now a second step is required, and technically you could do it now. Unmount everything, be quick enough, and remove the IHS, but it's just too difficult to access it, and too much could go wrong. That's why I would personally recommend to do it in 2 steps. That means we let it cool down to a certain degree, maybe like 50 degrees Celsius until we can touch it. Then we take everything apart, we put the CPU back onto the heating element without the delidder until it's again hot enough to just take off the PCB. Fast forward 15 minutes later, it heats up a lot quicker because the CPU has so much less mass than before. Temperature sensor has contact with the IHS. I'm waiting again for 160 degrees Celsius, 165, and then I can take off the PCB hopefully. I exceeded the intended temperature a little bit. I think I reached like 180 degrees Celsius, which is still fine. And you can see a lot of indium solder sitting on the IHS. And here we have our delidded Intel Arrow Lake CPU. First look, no damage on the SMDs, looks all good. Just the removed glue and the remaining solder in the center. I will now proceed remove most of the glue, scratch it off, and then also remove most of the indium solder and remove the rest with liquid metal. And the majority of the glue is removed, so time to scratch the indium. And with the liquid metal, I plan to remove the remaining indium. We'll leave it on there for maybe 15 minutes. For the CPU, we first want to check if it's still alive. So putting it into the socket, we cut a cryo sheet into the perfect size, put it on top, then place the original heat spreader back on it, and then also an AlphaCool Core 1 water block, because with that we can easily just check if it still works. And as you can see, it is the case. So we have a successful boot, CPU is still alive. That is awesome for us. Now, 1 month later, I'm here in Taiwan. I'm currently testing 285K CPUs here at ASUS HQ, and they also gave me the opportunity to delid another retail CPU, because the CPU that we used so far in this video was an early ES that was only able to clock to like 4.7 gigahertz, and I also wanted to test it with more samples, like a bigger sample size, simply to be sure that the delidding process works, and it also works with multiple CPUs. Like 1 out of 1 it's fine, but it doesn't really give you a bigger picture, because Intel still, they expressed their concerns doing it the conventional way without heating it up, that it might damage parts of the CPU. And meanwhile, I also finished the entire delidding heater. We can take a look at that in a second. And then this CPU that I'm currently running, this 285K, I'm just getting some baseline temperatures so we know what kind of temperatures to expect without delidding, and then we can also get comparison after delidding with a normal retail CPU. In this configuration, the 285K, it's slightly overclocked. It's running 5.4 across all of the P-cores, which is kind of the stock clock, but only as long as the P-cores stay below 70 degrees Celsius because of the TVB, the thermal velocity boost. The E-cores are slightly overclocked from 4.6 to 4.9. So in this situation, in this state, that's the kind of temperature that I'm seeing. It's a bit difficult to just get an easy overview because the P-cores and E-cores are mixed here, like the 2 P-cores on top and then the E-cores underneath, P-cores in between. But you can see the first 2 P-cores are maxing out below 80 degrees Celsius, and then the middle P-cores like 90 degrees Celsius max, and then we have middle E-cores in the mid 80s. And I will just simply take a screenshot of this, like a picture, and this will be our comparison value for later. We made quite some progress on the delidder and heater as well. So the delidder almost final, just missing laser engravement. Same goes for the heater. We now have the temperature probe sitting in here that can make contact with the delidder, or in the second step with the CPU. We have the heater inside here, which is without the aluminum case, looks like this. It's a 50 watt, 12 volt one that we got made for this. And then we have a controller that we also got made for this, and also the case. The case is, again, not final, it's 3D printed for now, and the final one will be CNC milled to look nicer. And here we have the controls. I just want to show you quickly how it works. Power supply for the control unit is USB-C, has to be at least 65 watt because the heater is 50 watt. And we don't include USB Type-C PSU because it would make it even more expensive. And I just hope that a lot of people have USB PSUs at home, and if not, it might just make sense to also get one. You can use it for charge your phone, or like this is my normal notebook PSU charger. And once you plug it in, you can see the configuration. So the stock configuration, it's reading out one temperature, is T now. That's the temperature of the delidder right now. And then T set is the value we want to reach, which is stock configured to 165 degrees Celsius. And we can change it with the buttons on top. So we can increase it or decrease it if we want to change that value. And once we press the button on the right, heater switches from off to on. And then you can also see that it's heating with 54 watt, and it will keep heating until the T now reaches a T set of 165, and then it will power off, and then hopefully we can proceed with the delidding steps, and this will be the same as the one that we previously did. So I will now get the retail CPU out of the system, put it in here, and we will just try another one. Professional fire resistant surface.
Yeah, don't try this at home.
Only at ASUS HQ. First, placing the CPU into the delidder again, everything assembled into the heater. Make sure that the temperature sensor is well connected with the backside of the CPU. As you can see, I also added a little bit of thermal paste. So, switch on the heater. And wait. So far looks good. We also added another thermometer to compare temperatures. It's not exactly the same location, but it's very close, so that should be in line. As last time, we had to wait about 15 to 20 minutes until it reached 165 degrees Celsius. Yeah, should be it. I let everything cool down to about 30 degrees Celsius, took everything back out, so CPU out of the delidder and the heater, and again, as you can see in the state, the IHS is shifted, but it's sitting firmly on there. That is because the glue is loose, but again, because we are below the melting point of the indium is solid, so it has to be heated the second time. I put the CPU on the heater with the IHS facing downwards. Make sure that the temperature sensor is well connected to the IHS. Again, with a bit of thermal paste, then again heating up to 165 degrees Celsius, which takes 1 or 2 minutes, and take off the PCB. Of course, I forgot the acrylic pieces to scrape off glue and indium, but I repurposed one of Elmore's acrylic cases. Just added liquid metal again. We'll probably have to repeat this 2 or 3 times to just remove all of the remaining indium. I skipped some steps. I meanwhile cleaned the CPU, put liquid metal on it, put it in the socket, mounted the water block, and now without the loop attached, I just want to run it quickly, boot it up, see if the CPU is alive. Oh. Well, at least it's not doing 00 straight away, so could be something. Yep. Nice. Time to attach it to a loop then. I think I forgot to mention in the previous clip which cooling I was using to get the baseline numbers, and it was this 280 AIO from ASUS. Yeah, it's maybe a bit questionable shape, so maybe if you would use a more recent one, might be like 5 degrees Celsius colder, but yeah, can only use the tools that I have here. So everything back up and running now with a custom water cooling loop, a 360 radiator, D5 pump from EK, all connected to the Mycro. I'm going to repeat it. I just tested it already, and it's, yeah, the temperatures are insane. Exactly the same scenario as before. I just reloaded the same BIOS profile. P cores are running 5.4, E cores are running again 4.9. Same voltage, same everything. Just rerunning this and pay attention to the temperatures. You will see it's a lot lower, like a lot. Previously, we were peaking out P core 12 at 90 degrees Celsius, and this is now even below 70. I mean, this is like 50 to 60 degrees Celsius, which is insanely cold compared to previously. Again, roughly the same performance, some fluctuation as usual, but yeah, very cold. Now, I also have headroom to keep clocking the CPU up, because previously with 90 degrees Celsius on the P core, that was just hitting the limit. I could not increase the performance more on the CPU. I just didn't have the thermal headroom to increase the voltage further, which I want to try now and maybe squeeze a bit more out of it. Did some fine tuning to the system. P cores are now 5.716 because you can adjust the P cores in 16 megahertz steps. E-cores are still sitting at 5.1. I'm struggling to get these higher, but this is working. Just running first with HDBeenDope, still running and active, so you can see the temperatures didn't really change a lot. It's still very cold. P-core 12 is still the hottest with 70 degrees Celsius. And even with hardware info open, it's like 46.7K. And running again without HDBeenDope. I mean, look at this, it's 47.1K. It's in the end like an 8-core CPU with a lot of strong E-cores, but that is a crazy score for water cooling. Another month later, finally the Intel Arrow Lake CPUs will be available at the point of you watching this video. And also our Grizzly products will be available, so that is for contact frame, for the Mycro DirectEye Pro, the DirectEye block, and also the delidder, but not the heater unfortunately yet. So this white thing with the heating element inside and with the control unit, they will be delayed by about 2 to 3 weeks, simply because the supplier of our PCB mixed something up from VCC to ground. So we had to order the PCBs again, so we had a small delay there. But apart from that, everything pretty much worked out according to plan. I meanwhile delidded a lot of chips for testing, all of the CPUs except for one of my 285Ks, because I had to keep one stock for testing. And within all of these CPUs, I figured that they all seem to be very convex when it comes to the die for whatever reason. At least delidded, you can easily see that the chip is slightly convex. And I measured 2 of these chips and you can see they're pretty much identical. So from the corner to the center, we're talking about 0.1 millimeter difference. And yeah, that is too much of just being something that happens one time. And because all the CPUs seem to be very identical or close to each other, I think this is maybe a result of the manufacturing process. At the point of mounting the DirectEye water block, it will bend back the CPU, at least to a certain degree. I can't measure how far that is, because that's pretty much impossible to measure it while it's being mounted. But we also tested this on this CPU 10 times. And the CPU is still alive, so at least I have that covered. But I can't tell you if there might be any kind of defect or like material fatigue if you mount it, I don't know, 50 times and do this bending and bending back motion. I can't guarantee that this won't ever break your CPU or damage it. It could be fine forever, but it also can't. I think we will figure that out together probably over the next year. We should also quickly talk about the PCB, the chip, and the components surrounding it when it comes to the height. The SMD components on the top left, they measured a height of 0.35 millimeters. Bottom right, they are a little bit smaller, so they're 0.3 millimeter in height. However, bottom left, I measured 0.45 millimeter in height. And now we have to compare that to the chip. And at least the chip corner is something below 0.4 millimeters. And as I showed you previously, because it's slightly convex, it's not that easy to measure. And in the center, it will be something about or above 0.4 millimeter. In any way, though, the components on the bottom left with their 0.45 millimeters are higher than the chip in the middle. This means that any normal cooler for DirectEye wouldn't work. So if you just mount a normal cooler on top, it would touch the SMDs before it touches the chip in the center, and thus probably short and kill or damage at least your CPU. So if there is going to be a DirectEye frame, I can just tell you that from Grizzly side, we won't make one because of that. It just doesn't make any sense. But if somebody out there is going to make a DirectEye frame, you have to keep that in mind, that any normal cooler without modification will not work. With about 0.4 millimeter die height, the Intel 285K has an incredibly thin chip, because you have to keep in mind that is already about 60 to 80 micrometer below a 14900K, which has a monolithic die. But as you all know, Arrow Lake, because it features the base tile and then the tile sitting on top, it's 2 layers. And then two layers formed with 0.4 millimeter means that probably, I don't know the exact numbers yet, that's something for a follow-up video, but let's just assume that it's 50-50 shared. That means that the base tile would maybe be 0.2 millimeter and the compute tile another 0.2 millimeter. And that would mean that the compute tile where the cores sit on the 285K is about half as thin or half as thick versus a 14900K. And that definitely is beneficial for the temperatures. I mean, you probably saw this in the past, that you can do die thinning, just grind, polish down the chip to make it thinner, to have a quicker heat transfer from the compute tile or from the cores to the cooler. So that definitely helps, and that is surely one of the reasons why the 285K is so cold, even under high load. There's one more thing I wanted to test with this 285K retail. It's the same one that you saw in my footage where I was at ASUS. I just want to mount it again, do testing with a proper normal water cooling setup. I have the Mora sitting underneath the desk, and then I want to check what happens if I disable the E-cores, if I can clock the ring higher on the CPU, and if this helps getting the CPU some extra performance. Quick look at the cooling structure of our Mycro DirectEye Pro water block. It is a hybrid structure, what we call it. So on the bottom, it is less dense. On the top, it's more dense and deeper. So the fin area here is bigger for the power or the concentrated hotspot that is on the compute tile. And you can also see how we shifted the entire cooling area a little bit upwards and to the right. So you see it's not fully centered, and that's just to account for the shifted hotspot on the compute tile. So it sits directly in the center of the hotspot, and that is just a non-nickel coated one, and this would be a final one that is then nickel coated. Already applied the liquid metal to the CPU. And also liquid metal applied to the water DirectEye block. Pretty sure the cooler would look much better with different fittings and maybe like hard tubing, but generally I think it just suits the Apex much better than the Black Edition. There's not much that the 285K can do reliably, but in this very specific scenario in Cinebench R23, the CPU with manual overclock and bypass mode is actually quite solid. So first of all, taking a look at the performance, which here without hardware info is about 47,500 to 47,600 points. Now with hardware info open, the P cores are clocked to 5.73, E cores are at 5.15. That is pretty much the max this CPU can do. It's just an average retail. It's nothing binned or anything. Temperatures are crazy low. Under load between 50 and 60 degrees Celsius. Highest P core, I already did the German take, so ran this probably like 5 times already. And you can see the highest is 66 degrees Celsius. I think that is pretty cold. Again, CPU package power draw is reported wrong. I already explained that in my last video. If you want to check the correct one, you go down here and check the P out of the VRM, and there you can see it's about 230 watt under load, which I think is quite impressive. At least this very specific scenario, so high multi-core load like Cinebench in the bypass mode, 230 to 240 watt for 47,000 points. I think that is actually quite nice. The ring was running at 4G in this scenario. I just want to check now if I disable E-cores, if I can clock the ring significantly higher or not. So here, disable all the E-cores. And here we just go to 45 cache, see if we can do that. If it doesn't work, it's just not worth it. Like for 100 megahertz ring, you're not going to disable the E-cores. It is also running Cinebench, here 4.5 ring. The temperatures don't really change for the P cores. That's simply because the power density of the core itself is already quite high, and what is sitting next to it doesn't really have a big impact on it. But we can also check power draw, which you can see here. P out is about 140 watt. So you only save about 80 to 90 watt by disabling the E-cores. And multi-threading efficiency will suffer badly. 18,000 points, that is not mind-blowing, right? The 4.5G on the ring was also the max. 4.7 would not even boot. So I don't think there is any like magic setting that pushes the 285K or Arrow Lake to suddenly perform well. I think, the platform is just what it is. I don't think there is any magic change you can do to suddenly make the platform perform good. Quickly back to delidding and the entire process now that we gained a lot of experience. I know of 10 cases now of delidded 285Ks that are working with exactly this method of heating up the CPU. And I also know of 2 cases which were done without heating it up and where the CPUs were damaged. That kind of shows that there seems to be something to it, what Intel said, that it might cause damages if you stress the die too much with mechanical force. So that is something you should definitely keep in mind. And I would definitely recommend that you use this because it's a very controlled environment and you can set the heat, you can measure the temperature. But we will still sell it separately. So you can just also buy the delidder itself and not use the heater, because depending on your equipment, an oven at home could be fine enough. If you have like hot air circulation inside, then you just set it to 170 degrees Celsius and just leave the delidder with the CPU inside for maybe 20 or 30 minutes until you know that it reached at least 157 degrees Celsius, which is the melting point of the indium. So you can do the first step of delidding. Just move it once and let it cool down. But you have to make sure that you bypass the 157 degrees Celsius. Otherwise, yeah, you might still stress the die too much. So you definitely have to control that. Afterwards, you let it cool down, take out your CPU, exactly how we did it earlier in this video. And in that state, the IHS will be just shifted to the side and we loosened the glue in that state. And then you have to heat it up again, same as I showed you, to eventually take off the PCB. And for that, we made this tiny tool, which will be a lot cheaper than the heater. If you want to go with the oven or like the air fryer method, that should all work. You can just put your CPU with the shifted IHS, which will just solidify again the indium, so it will still be stuck. You can slide it in here, heat it up again, and then just once you bypass 157 degrees Celsius, the IHS will drop down, and then you will be able to take out the PCB once it's again cool, and you can just take it off. With this method, you can and you should measure the temperature if it's possible, but it should be fine if you just, have an eye on it, and then see if the IHS dropped down or not. But you should generally be careful when heating up the CPUs. We are recommending 165 degrees Celsius. I personally tested up to 180. It was still fine, but I don't know at which point it will become dangerous for your CPU. That could be maybe 200 degrees Celsius or above 200 degrees Celsius. I didn't want to find out now. And so that's why you should be careful and always track the temperature. That's also why I would advise not to use the iron method. I saw it a lot, especially with AMD AM5 CPUs. It's fine if you track the temperature directly on the PCB, but without measuring the temperature, I can't really recommend it because there's always still a risk involved of damaging your chip. The heater will be available, as I said, in like 2 or 3 weeks, and it will cost 90 euro. And I know that's quite pricey, but we have multiple like CNC milled parts and again CNC milled parts and the PCB software development and all that. And it's a low quantity product. So yeah, unfortunately it's a bit more expensive than I expected. That's why, yeah, we offered that we just sell it separately, the delidder. So you don't have to buy it. You can do it because it's more controlled. You can also get the smaller one, which we probably call the melting mate. That is the final version of the heater. There's also a warning sticker. Obviously, you will peel it off. I just kept it on there for now. But make sure that you put it on a fire-resistant surface. And yeah, peel it off before use and use gloves to not burn your paws. There's also the temperature sensor now that can make either in the first step contact with the back of the PCB or second step with the IHS of the CPU. You put the CPU into the delidder as known according to the triangles, and then you place it on here. You can, or you should apply thermal paste on here, which will also be included in the heater. Place it on here. Now make sure that the temperature sensor has good contact to the back of the CPU, to the PCB. Ideally, you also add some thermal paste on here to just make sure that the contact is really good from the temperature sensor to the PCB itself. And then you just close it. Tighten the screws, just hand tight is fine. This is the control unit. Now final state, you have 3 buttons, up, down and confirm. Display in the center, and it is powered by USB Type-C. You need at least 65 watt and you need 20 volt and 3 amps. If it's only 12 volt like this one, it will show not enough and it requires 65 watt at 20 volt. With my Lenovo USB Type-C charger from the notebook, it just works fine. Plug it in. You can see USB is now 20 volt. Target is 165 degrees Celsius. You can no longer change the target temperature itself with these buttons, at least in the stock condition. You can only switch it on with the confirm button. And then you can see now heat counts up in seconds. You can also see that the power output is increasing until 50 watt. And now also the temperature increases. Heat is now counting up to a max of 1800 seconds, which is 30 minutes. That's just a safety measure. So maybe if you forget to turn it off, then it would turn off automatically after 30 minutes, or until it reaches 165 degrees Celsius. If 30 minutes was not enough to heat it up, which shouldn't be the case, but I don't know, could happen maybe if you're in Antarctica or something, then you just reset it again and the counter will start again once it reaches 165 degrees Celsius. There is also a hidden config menu. If you want to adjust anything, you have to hold down the up and down buttons, both at the same time. Then you plug it in, keep the buttons pressed until it starts. You can release it. Now you are in the config menu. And here you can, if you scroll up, you find the firmware version. And if you go down, you can adjust anything. Like the set temperature, you can adjust it to 170, for example. You can lower the power to, let's say, 45 for whatever reason. If that is something that has to be done in the future, it is fully configurable. Then you just go back down, save, and then if you plug it in again, you will see that it saved the settings. Now it would be 170 degrees Celsius, and if I switch it on, then it would stop at 40 watt. So it's fully configurable. I'm not sure if that will be required, but yeah, we just made it just in case. I would say overall, Arrow Lake delidding got a little bit out of hand. It's the most complex delidding I had to do so far. I still enjoyed making all these tools and verify it and finally get it to work. Also pretty close to launch, I would say. And still, if you do all that, I think the reward is pretty nice. Like a 285K delidded direct die, it has very nice temperatures. So even high load, you are able to usually do like 60, 65 degrees Celsius and do a very solid overclock. So I think it's quite beneficial and also rewarding. And yeah, I hope you enjoyed it so far. I hope you enjoyed this journey with me to see how things like this are developed, how much work and effort actually goes in it, but also how much you can do with it, which I think can be a lot of fun. If you're interested in that, you will find all the links in the description for the Thermal Grizzly products. And I hope you enjoyed it. Thanks. See you next time. Bye-bye.